All right, example 5. Trail ride. Hosts of a ranch estimate that percentages of guests who are interested in trail rides to be 70%. So that's given us the p-value, that's the probability of success, we'll say, is 70%, which we could list as 0.7 or 0.70. Now, our probability of failure then would be 1 minus the 70%, which would be 30% or 0.3. It says, in order to have a trail ride, there must be at least 10, but no more than 15 riders. If there are 17 guests at the ranch, what is the probability that there will be one trail ride? Okay, so we need to come up with, out of these numbers, which one is our sample and so on. How many guests are there? The answer is there's 17 guests. So here's our deal. We have 17 guests, but we want the probability that the random amount of samples to be between 10 and 15. So let me write out the probability this way. We want to know the probability of having between 15. Oh, I'm sorry, between 10, but no more than 15. Having at least 10, that means you can be equal to it. But no more than 15, which means you could have 15. So I need to put 15 equal there. So this is the probability that I'm looking for. And so this time, instead of getting to the end and saying, okay, now there's correction factors, let's go ahead and check out the correction factors. So if you are equal to a number, notice what you do. Let me start here because I wrote it, or let me start. We first said we are greater than or equal to 10. Which means you need to take that 10 and subtract 0.5. So the first value would be the probability of 10 minus, I should have wrote it out completely the first time around, is less than or equal to x. And now we're going to say less than 15. And so let me go find that probability. What's the probability of being less than or equal to 15 is I would add a 0.5. So I need to add a 0.5 here. 15.5. So my actual probability, this is the correction factors. When I solve this, we're going to be looking for the probability that the random variable here, this x, is, that's supposed to be a 5, 9.5, sorry. That 9.5 is less than or equal to x, which is less than or equal to 15.5. And I realized there, let me correct this, I'm sorry. I meant to put the correction factor, which is plus 0.5. Okay, so there's my correction factors. That's the probability I'm looking for. So let's look at this over here. I'm gonna change these values. Let me just turn this one off because that's not the values I want anymore. We're gonna say that there are 17 guests. The probability of them wanting to ride is 70%, which means it's 0.3% or 30%, not 0.3%, I'm sorry, 0.3 the total, or 30% will not want to ride. And so now when I look at this normalized distribution of the binomials, I want to know what's the probability that there are a minimum of 10, a maximum of 15. If I put in those numbers, I get the wrong answer. That's not the right answer. 79% is not right. Why is it not right? Because I need to use the correction factors. I need to actually say from 9.5 to 15.5. The actual probability here is going to be approximately 0.869 or 86.96%. So almost 87% chance that they'll have one trail ride. Now you might be saying to yourself, oh, Mr. Voorhees, this time you didn't do all that other math. Well, you don't have to using the calculator, but if you wanted to, remember the values you first do is you need to check if n times p, which in this case was 17 times use this to 0.7 is greater than 5. So when I check this out, let's see here. 17 times 0.7 is 11.9. So that was good. Which that's greater than 5. And you would also check n times q, which this one's going to be a smaller number. Let's see what 17 times 0.3 is. Oh, 5.1, barely made it. So this is if you were going to be using a standard normal, you'd need to go through this process first. Now we would say, all right, this happens to be the mean. The mean here is going to equal n times the probability. This number of samples times the probability, which we had is 11.9. And the standard deviation, we would do the square root of the n times p times q, which in this case, let me just write it out, n times p times q, which would equal the square root. We had 17 times 0.7 times, oops, forgot the parenthesis, 0.3. And let's see what this value is. This is our standard deviation. So if I want to know the square root of 17 times 0.3 times 0.7, the order doesn't matter when you multiply, unitive property there. We get 1.889. That's our standard deviation. 1.889. Whoops, 889. There we go. And now if you wanted to find your z value, the z would equal, the mean we would be checking for, you would need to use these two x values. So we'd have two z values. Z1 would be 9.5 minus 11.9 divided by that 1.889. That would be your first z value. Your second z value that you would have to find for this particular problem, you would take a 15.5 minus the 11.9 and divide that by the 1.889. And if you did those two things, you would be able to use just a standard normal when solving this. So let me say here, 9.5 minus 11.9 over 1.889. This is a z value of negative 1.27. Some people call this a z score. Negative 1.27. And over here, let's see what this z-score value would be. If I change this to a 15.5, I get 1.91, 1.91. And so if I use the standard normal from, let me just type these in here, negative 1.27 to 1.91, you can see we get the same number here, basically the same number. So I should have just come up here and done the standard normal. So again, these z values would be if you were using a standard normal distribution. That's what a standard normal distribution, that's how you would represent a normal distribution with the mean of 0 and a standard deviation of 1. These would be the z values you'd use to find that probability. Okay, so I gave that to you a lot quicker using the calculator. And then over here, as you can tell, it can kind of get confusing at times going through all the numbers. Here's one for you to try. I'd recommend just using the calculator, but do whatever is best for you. Example 5, pause the video if you need to.